Welcome to week 8, Model Tuning and Optimization. Our week will start with day 1 introducing to hyperparameter tuning. Day 2, we will look at grid search and random search. Day 3, we look at some advanced hyperparameter tuning with Bayesian optimization. Day 4, we'll be looking at regularization techniques for model optimization. Day 5, we'll be looking at cross-validation and model evaluation techniques. Day 6 will be about automated hyperparameter tuning with grid search CV and randomized search CV. And finally, day 7 will be our optimization project where we will be building and tuning a final model. So let's get started with week 8.
Welcome to week 8, day 1, Introduction to Hyperparameter Tuning. First, let's go ahead and understand the difference between parameters and hyperparameters. So first, what are parameters? Parameters are values learned by a machine learning model during training. They are adjusted to minimize the loss function and optimize predictions. Examples of parameters include the coefficients in linear regression, also the weights and biases in neural networks. We've used some of them already, but we're going to use quite a lot in the coming few weeks. Now, what are hyperparameters? Hyperparameters are setting defined before training that influence how the model learns from data. They are not learned from the data, but instead control the training process. Examples can be the tree depth, maximum depth of decision trees, learning rate, step size for gradient descent, and number of estimators, number of trees in an ensemble model. And we have used quite of these hyperparameters in the last week. And now we will dive deep into more of these. Now let's talk about importance of tuning hyperparameters. Now why tune hyperparameters? First, it improves the model performance. It's optimal hyperparameters that help models generalize better, reducing overfitting and underfitting. Enhance efficiency. Proper tuning can reduce training time and computational resources. Adapt to problem specific needs. Tailoring hyperparameters ensures the model fits the dataset's characteristics. And these are some of the things that we have already noticed. Now let's talk about common hyperparameters in popular models. Now, based on the things that we have done, especially with decision trees and random forest, we know that we've used the max depth, which limits the depth of trees to avoid overfitting, min samples split, which is the minimum samples required to split an internal node, and number of estimators, which is total number of trees in a random forest. Now, gradient boosting models, if for example we used XGBoost and Light GBM, we have learning rate, which determines the contribution of each tree. We also use subsample, which is the fraction of training data used to train each tree. And then we also used max depth, which limits the complexity of individual trees. Let's talk about neural networks. In neural networks, we have the learning rate, which is the step size for weight updates. We also use number of layers, which determines the depth of the network. And then we have batch size, which is number of samples per gradient update. Now, with all this knowledge, let's go and jump into a quick hands-on exercise where the objective is to train a model with default hyperparameters, evaluate its performance, and manually adjust a few hyperparameters to observe their impact on results. Now, the dataset we'll be using here is Iris dataset, which is an optimal dataset already, but we'll use it because it's a multi-class classification problem and it will be a good sample to walk through. But we will not be seeing the impact on the results with hyperparameter tuning because it's always optimal. So, but it gives you an idea or a guide on how to approach this problem. So step 1 is to load and explore the dataset as usual. So I'm going to go ahead, create a new file, Python file, save it in my day 1. I'm going to call it day 1 underscore samples or exercise 1. And here, first, let's go ahead and get the data set. So I'm going to say from sklearn dot datasets, I want to import load iris. Next, I'm going to say from sklearn dot model selection, I want to import train test split. Also want to import pandas as PD. Now let's go ahead and load the data set. First I'll say data equal to load iris, and then our features and target, I'm going to say data dot data and data dot target. Oops. Next I will split the data set. Now to split, I'll get x underscore train, x underscore test, y underscore train, and y underscore test. Now this I get from train test split, and I can say x, y, test size equal to 0.2 and random state equal to 42. So once I have these, I'm going to go ahead and display some data set info, and for that I'll say print f feature names. If you already forgotten it, that's why it's always good to brush up on these, especially when you're working on a bunch of different data sets on a daily basis. Names. Next I want the class names, and that is data dot target names. There you go. Save it. I'm going to run it here. Let's make sure I'm in the right folder. Python day 1, and looks like I have a typo here. Feature names. Let's try it again, and there you go. We have our, let me clear it so we don't see that error. Here you go. Feature name, sepal length, sepal width, petal length, and petal width. Class names are Setosa, Versicolor, and Virginica. So those are our targets. Now let's go ahead with step 2, where we will train a model with some default hyperparameters. In this case, we'll train a random forest classifier with the default setting and evaluate its performance. I am going to say that first I need the random forest classifier. For that, I'm going to say sklearn dot ensemble import random forest classifier. From sklearn dot metrics, I can say import, I need accuracy score, classification report. So that's once I have that. Next I am going to say train random forest with default hyperparameters. Also, I've seen that I've not used panda because I already have the data set locally, so I don't need that. If I need it, I'll add it again. I'll say rf underscore defaults default is equal to random forest classifier, and I'm going to use random state equal to 42. That's all I have to do here. And I'll say rf underscore default. Now I will fit with x underscore train and y underscore train. Next, let's go ahead and predict and evaluate. To do that, I'll say y underscore predict underscore default equal to rf underscore default dot predict and pass it x underscore test. Next, I'll say accuracy for default equal to accuracy score and pass it y underscore test and y underscore predict default. So we have our things here. Now let's go ahead and print them. Say print default model accuracy is accuracy default 0.4f. Next, I'm going to say print /n classification report /n, and here I'll say classification report, and it needs the same y underscore test and y underscore predict default. So perfect. So this is our training a model with the default hyperparameters that we have. So let's go ahead and run it. It'll give me the feature names, and then it says default model accuracy is 1.2. It's pretty good. What if I use the breast cancer data? So this has 0.98, 0.7. So it's a little bit lower than the actual this one, the iris database. So I'm going to change it to this just to play with it. So I have that data, I have predicting here. Next step is to manually adjust the hyperparameters. Now we're using the default ones here. So let's go ahead and modify some key hyperparameters such as n estimators and max depth to observe their impact on the model performance. So I am going to say train random forest with adjusted hyperparameters rf underscore tuned equal to random forest classifier, and this I'm going to give the hyperparameters. First I'll set the n estimators equal to 200. I've already seen in last week that giving the maximum is better. You can increase the number of trees if you want. Max underscore depth equal to, I'll give 5, so that's the limit of the tree depth, and then random state, so it generates the same data every time I run it. Rf underscore tuned dot fit, and I'll fit x underscore train comma y underscore train. Now next, let's go ahead and predict and evaluate based on the hyperparameter setting. So I am going to say here y underscore pred underscore tuned equal to I'll say rf underscore tuned that you created above dot predict, and I'll pass x underscore test to it. Next I'll go and say accuracy, not default this time, but tuned equal to accuracy score, give it y underscore test comma y underscore pred underscore tuned. Now let's go ahead and print the results. I'm going to say f of tuned model accuracy is accuracy tuned 0.4 f, and then I'll say print /n classification report /n is classification report, pass it y underscore test and y underscore pred tuned. That's good. It looks good. Everything is tuned. And now we can compare those results here and see how it looks like. So I'm going to save it. It's already cleared. So I'm going to run Python day 1 and make it a little bigger so we see the difference. So if you see, before it was 9649. After the tuning, it's also 9649. And these are my different numbers for different parameters. I can go ahead and increase the number of trees, number of estimators. Let's see if it increases 9649. I think that's the best it can go. So this is the actual process. First, you can use a particular model, or in this particular random forest classifier, train it, and then you can also tune the hyperparameters and test if it makes any difference. Sometimes it does, sometimes it doesn't. So I hope you were able to follow along, and if you have any questions or had any issues running this, let me know. So just to summarize, today we went and understood the difference between parameters and hyperparameters in machine learning models. We recognized the importance of hyperparameter tuning for optimizing model performance. We did some hands-on where we trained models with default and manually tuned the hyperparameters. And we learned how hyperparameter adjustment might influence key metrics like accuracy and classification report. In our case, we did not see that, but it does if you use some of the data that is available. But if you had any issues or problems and have any questions, let me know and I'll get back to you. Day 2, Grid Search and Random Search. Today, let's go ahead and first let me introduce you to Grid Search and Random Search. What is Grid Search? Grid Search is a method of hyperparameter tuning that systematically evaluates all possible combination of hyperparameter values within a specified grid. Now, how does it work? You define a range of values for each hyperparameter, train and evaluate the model on each combination of hyperparameter values, and select the combination that yields the best performance. And we've seen some of this early in the earlier weeks, but we're going to go more deep into it today. Now, what is random search? Random search is an alternative method where hyperparameter combinations are sampled randomly from the specified ranges. Now, how does it work? You define ranges or distributions for each hyperparameter. Next, you randomly sample a specified number of combinations. And then finally, you train and evaluate the model for each sampled combination. Let's look at some of the pros and cons of each method. I've created a tabular method for it where we're going to look at features, grid search, and random search. For example, exhaustiveness in grid search evaluates all combinations. In random search, randomly samples combination. As per time efficiency, grid search is computationally expensive for large grids, whereas random search is faster for large parameter spaces. In case of exploration, grid search is limited to predefined grid, whereas random search explores more diverse ranges. The best use case for grid search is small parameter spaces, whereas for random search, it's large parameter spaces with time constraints. Next, let's look at the practical guideline on choosing the search ranges. What we do is first we start with a broad range. Use random search to explore large parameter spaces and identify promising ranges. Next, you refine with grid search. Narrow the search space based on random search results and perform exhaustive grid search for fine tuning. Finally, understand the model sensitivity. Some hyperparameters, example the learning rate, require fine granularity, while others, example the number of trees, can have coarser steps. Now, with this in mind, let's jump into our hands-on exercise where the objective is to implement both grid search and random search for hyperparameter tuning, compare their efficiency, and analyze the impact on the model performance. The dataset we'll be using again will be the iris dataset, which is the multi-class classification problem. So let's jump into and load and prepare the dataset. So I'm going to create a new file, save it as day2 underscore exercise. Here I'm going to from scikit-learn, I will get the data sets. As I mentioned, I'm going to use load iris. Now from sklearn dot model selection, I will import train test split. Let's go ahead and load the data set. Data equal to load iris. Next, I'll say features and target equal to data and data dot target. So I have that. Let's go ahead and split the data set. To do that, I will use the train test split and get x underscore train, x underscore test, y underscore train, and y underscore test. Again, from train test split, I'll pass x, y, I will say test size equal to 0.2 and random state equal to 42. There you go. So I have that. Next, let's go ahead and display dataset info. Again, I'll go ahead and print f of feature names, that is data dot feature underscore names. Next, I'll say print f of class names. For that, I'll say data dot target names. So let's, to make sure that everything is perfect here, go here and say python day dat2. Okay, I think I misspelled it, dat2.ex, and I have my feature names and class names. So perfect. Next step is to implement a grid search. So we'll define a grid of hyperparameters for random forest model and perform exhaustive search using the grid search CV, which means I'll need to import first from sklearn dot ensemble. I will import the random forest classifier. Next, from model selection, I need the grid search CV. Just import it there along with the train test split. And then I need metrics. In this case, I need accuracy score. You guessed it right. Next step is to define here the hyperparameter grid with some random values. Param underscore grid equal to, inside this grid I'll use first n underscore estimators, and this I will say I want to do a search based on 50, 100, 150. Next I want to say max depth I want to use is, in this case I'll say none, maybe no depth, 5 or 10, whichever works best. Next, I'm going to say the minimum underscore samples to split is equal to, so either do 2, 5 or 10 and tell me how it turns out. So now to initialize this grid search, I will first move it up. Let's keep it so we can see that. I'll say grid underscore search equal to grid search Day 3, Advanced Hyperparameter Tuning with Bayesian Optimization. First, let's go and see what is this Bayesian optimization. So here is an introduction to Bayesian optimization. First, what is Bayesian optimization? Bayesian optimization is an advanced method for hyperparameter tuning that balances exploration, which is searching for new regions, and exploitation, which is refining promising regions. Unlike grid or random search, which are blind to past evaluations, Bayesian optimization uses a probabilistic model to guide the search for optimal hyperparameters. Now, how does it work? We have a surrogate model which builds a probabilistic model, example a Gaussian process, of the objective function based on prior evaluations. Acquisition function. It balances exploration and exploitation by choosing the next hyperparameters to evaluate based on predicted performance and uncertainty. Then we have iterative refinement, which updates the surrogate model after each evaluation, refining the search. Now, why use Bayesian optimization? It's efficient for high dimensional and expensive to evaluate functions, and it reduces the number of evaluations required to find the near optimal hyperparameters. So let's jump into using libraries for Bayesian optimization. Some of the popular libraries that we use here are: first is HyperOpt, which simplifies Bayesian optimization for hyperparameter tuning. It works with fmin to minimize objective functions over a parameter space. We also have Optuna, which is a flexible and user-friendly library for hyperparameter optimization, and it supports dynamic search spaces and pruning of unpromising trials. Let's look at understanding exploration versus exploitation a little bit more. Now, what is exploration? It focuses on sampling hyperparameters from unexplored regions, and it's useful for identifying new areas of high potential. Whereas exploitation, on the other hand, focuses on refining the search around regions with known high performance, and it's useful for fine tuning near optimal hyperparameters. Next, let's talk about Bayesian's optimization's advantage. It balances these approaches using the acquisition function to minimize unnecessary evaluations while improving the results. That's why it stands out better than the grid or random search. Now let's jump into a hands-on exercise implementing this. The objective here is to apply Bayesian optimization using Optuna to tune an XGBoost model and compare the results with grid search and random search. So our steps that we will follow is: first, let's go ahead and create a new file, call it day3 underscore exercise. Now first, we will go ahead and load and pre-process the dataset. The dataset that we will be using here is the breast cancer dataset from scikit-learn as an example. So let's go ahead and go sklearn dot datasets import load breast cancer. Next, from sklearn dot model selection, I will import the train test split. Next, from sklearn dot preprocessing, I will import standard scalar, and then I'll import pandas as PD. Now let's load the dataset. To load the dataset, I'm going to say data equal to load underscore breast cancer. Now, the reason I'm do it over and over again every time is just for better practice. And if you're jumping in directly to this video, you can still follow along. And also another goal is for you to follow along and do it along with me. X comma y. But if you want to jump directly to the next steps, you can do that. Data comma data dot target. Next, I'm going to go ahead and split into training and test sets. So I'm going to say x underscore train, x underscore test, y underscore train, and y underscore test equal to train test split x comma y comma test size equal to 0.2 and random state equal to 42. Perfect. Now let's go ahead and standardize the features. So I'm going to say scalar equal to standard scalar. Initialize that. X underscore train equal to scalar dot fit underscore transform and pass it x underscore train. And for the testing set, x underscore test equal to scalar and just transform it with x underscore test. Perfect. So we have that. Now let's go ahead and print our training data shape. So we see how many items we have. X underscore train dot shape, and then also look at our test data shape. For that, I'll say x underscore test dot shape. Perfect. I'm going to run this. This is Python day 3 underscore ex. There you go. We have our training data set with 455 rows, 30 columns, and our test data shape is 114 rows with 30 columns. Perfect. So now we have that ready. Let's go and define a baseline XGBoost model. So we will train a baseline XGBoost model to establish a performance benchmark. So for that, I'm going to go up first, and from XGBoost, I will import XGB classifier. Now, if you don't have XGBoost installed, you can always say pip install XGBoost and it will install it for you. From sklearn dot metrics, I will import accuracy score. Looks like I'm not using Panda, so I'm going to get rid of that. And here now I'll say train a baseline XGBoost model. To do that, I'm going to say baseline underscore model equal to XGB classifier and pass it. I'm going to say first evaluate the metric equal to log loss, and then random state equal to 42. So that kind of initializes that. Next, I'm going to say baseline underscore model and fit it with the data. I'll say x underscore train, or train it with the data, however you want to call it. Next, I will go ahead and evaluate the model. To do that, I'll say baseline underscore preds equal to, we'll use the baseline model and predict the x underscore test. Next, I'll say baseline underscore accuracy. I will use the accuracy score and say y underscore test comma baseline preds. So that's what I am doing here. Next, let's take and go ahead and take it and print this thing. Baseline XGBoost accuracy is accuracy baseline accuracy 0.4 f. Perfect. Let's look at how it looks like right now without doing anything else. And baseline XGBoost is 0.9561. Perfect. Now let's go ahead and apply the Bayesian optimization using something called as Optuna. If you don't have Optuna, you'll have to install that by saying pip install Optuna, but I think I already have installed, so I'm going to say import Optuna, and then from XGBoost I will import, or I think I already imported the XGB classifier and my accuracy is there. So Optuna is all I needed here. So once that is done, I'm going to go ahead and define first I'll define the objective function for Optuna that is required. So for that, I'll say define I'll say objective and the trial data that is passed to it. Now we'll define the hyperparameter search space here. I'm going to say params equal to, now it needs a bunch of different things. First it needs a n underscore estimators. You can look at the documentation for this if you're interested in. And I'm going to say trial dot, from the trial I'll say suggest underscore int values for n underscore estimators from 50 to 500. Next, I'm going to say I need max underscore depth. For this, I will do the same thing. Trial suggest, instead of n estimators, I'll say max depth. And this time max depth can be anywhere from 3 to 100. That's what I'll ask it to do. Next one is learning rate. And I'll say trial dot suggest. In this case, learning rate is float. So I'm going to say float. And this will go from anywhere from 0.01 to 0.3. Next I need to do is for subsample. For subsample, I'm going to say trial suggest float subsample, and subsample can go from 0.6 to anywhere to 1.0. Next, I want to do it for column sample underscore by tree suggest. In this case, it's float again, and this float can be same 0.6 to 1.0. Next is gamma. For gamma, I will say suggest and float again gamma from 0 to 5. So that's good. Next I need is alpha, reg underscore alpha is trial dot suggest, and reg alpha 0 to 10. So it needs 3 parameters, gamma, alpha, and lambda. So I'm going to say reg underscore lambda is reg lambda 0 to 10. So these are all floats. Perfect. So that's done. Now next step after this is to train XGBoost model with the suggested parameters from above. So I'm going to say model equal to XGB classifier. I'm going to say evaluate underscore metrics. I'm going to use the same thing, log loss, and then random state equal to 42, same values that I always use, and then I'll say model dot fit x underscore train and y underscore train. So that's done. Next I will do is evaluate model on validation set. So this is where I'm going to say preds equal to model dot predict and pass x underscore test to it. Accuracy is equal to accuracy score and pass y underscore test comma preds. Then I'll return this accuracy. The thing that I forgot to add is this parameter. So XGB classifier, I need to train this with the parameter. So another thing that I have to add here is star params. This is where we pass the parameter to XG classifier. Now, once this is done, let's go ahead and go outside and create an Optuna study. That's what it's called, Optuna study. Study equal to, I'll say Optuna dot create underscore study. That's the function that they give us, and you can give a direction. I can say the direction is use maximize. and then study dot optimize. I'm going to say pass the objective, which is the function that we created, and n underscore trials equal to 50. So it will take this trials, add it as a parameter here, and run this, and it will give me the best parameters in the study best parameters. So to do that, I'm going to say best hyper parameters are print. So first I'll say give me the best hyper parameters from the study dot best underscore params. Next I'm going to say print the best accuracy based on those parameters, so we can compare study dot best underscore value. So there you go, that's all. Let's go ahead and clear this out and run it again. And it's going to run through those 50 trials that I've specified. As you can see, numbers are increasing, and it's completed. Now it gave me the best hyperparameters for n estimators 146, max depth 35, learning rate, this is the learning rate, subsample, call, gamma, alpha, lambda, and the best accuracy that comes is 9.964. And if you remember, the value that we got before was 0.9561, and now it's 9649. So you see it kind of improved the accuracy after using this Bayesian optimization using Optuna library. Now next step is to compare this with grid search and random search. Is it any better? Sometimes it is, sometimes it's not. So I'm going to clear it out, and I am going to go ahead and here from model selection I am going to get grid search CV to compare it with the grid search. So let's do the grid search first. I'm going to go ahead and define the parameter grid. To do that, I'm going to say param underscore grid. If you remember from what we've done before, we gave n estimators to be in between, let's say 100, 200, and 300 is what I'm going to give, because I remember it was a little bit higher value that it likes. Max underscore depth is equal to, I'll give 3, 5, and 7. Next, for learning rate, I will give the values of 0.01, comma, I'll say 0.1 and 0.2. Pick which is the best one. And then I'll give subsample. In this particular case, I'll say 0.6, 0.8, and 1.0. So now once we have this, let's go ahead and train the XGBoost with grid search. To do that, I'll say grid underscore search equal to grid, I'll call that function that we imported. Inside here, I'll say estimator equal to XGB classifier, and to this I'll say evaluate underscore metric equal to log loss. Next, I need to give the random state equal to 42. Now here we don't do the we don't give the parameters here, but in this it's a separate parameters grid equal to parameter grid. So it's a separate parameter that we give to this particular function. Next, I need to pass the scoring that I'm interested in is accuracy. I give the cross validation, which is this time let's reduce it to 3, and verbose equal to 1. So perfect. So I have all my data here for the grid. Now let's go ahead and run this or fit the model grid search dot fit x underscore train. So train it with x train and y underscore train. So that's Ready? Our grid search is ready. Now let's go ahead and look at best parameters and accuracy with this. And I'm going to say print grid search best parameters equal to grid search dot best parameters, and then for accuracy I'll say grid search best accuracy is grid search dot best score. Perfect. I'm going to give some slash and slash and slash in so we see the difference between the two. And also, while we are at it, let's also implement the random search CV. It's almost same as this. So for I'm going to define the parameter distribution for my parameter dist, and n estimators I'll give the values of 50, 100, 200, 300 and 400. For max depth I'll give 3, 5, 7. Let's add one more to it, comma 9. Learning rate I'll say 0.01. Let's add 0.05, 0.1, 0.2. Subsample we have 0.6. Let's add 0.7, 0.8, 0.9. Why not? Right? And then let's also give call space call sample column sample underscore by tree. For this I'll use same numbers as this. There you go. So that's ready. Now let's go ahead and train the XGBoost with this random search that we have imported. So to do that, I'm going to first start with random search parameter variable and then say random search CV. The estimator that I want to use is XGB classifier, and I'll say eval underscore a metric equal to log loss, and then random search or not search random state equal to 42. Next parameter that we need is the distribution. So I'm going to say parameter distribution equal to param dist that we've created right above here. So that's what I've given there. Next, number of iterations that I want to run is, let's say 50. Scoring equal to, I'll say accuracy. Next, I need to give the CV cross validation, give same number 3. Verbose equal to 1. Next, I want to say random state, since it's a random search, I'll have to give a number 42. Random search dot fit, pass it x underscore train and y underscore train. Perfect. Now let's go ahead and print out the best parameters and accuracy for the random search. So I'm going to say print. Again, I'll give some space slash and slash and slash in random search best parameters equal to random search dot best params. And then for the accuracy, random search best accuracy equal to random search dot best score. Perfect. So I have all the three ready right now. So let's go ahead and compare the results for all of them. Save it, go run here. And it's going to run, take some time, go through it. But I can see here the baseline is 0.9561. So I can take that and type it here. So this is my baseline XGBoost accuracy. Let's go all the way to the down. Now here, this is best accuracy with hyperparameters that we have given 0.9649. Now, where did we? Oh, this is actually not. This is it best accuracy that we have printed? Yeah, here study based on the based on Optuna. That was the best accuracy. Now it's doing the grid search, and grid search best accuracy is this. So I'm going to go ahead and put it down here, 0.975. So with grid search, it's much better than the Optuna. So I'm going to say this is Optuna, and now it's doing the random search. So we'll probably be seeing the random search best accuracy next, which is this value 9758. 9758. So I think this is the winner here out of the four of them. So this is how you can kind of test different ones and use whichever is best. So first is default. This is as per Optuna, this is as per grid, and the final, the random search. So in our case, random search has the best accuracy, so we can use that model. But depending upon your data set that you have, you should use that particular data set and check the accuracy and then use that model. Just to summarize, today we understood the importance of hyperparameter tuning in improving model performance. We gained practical experience with Bayesian optimization using Optuna, and we compared the traditional search methods, which are grid and random search, with Bayesian optimization. And we learned how to interpret and analyze the hyperparameter tuning results effectively to find out which is the best one to use for our use case. So if you have any problems or had any issues while implementing this or have any other questions, let me know in the messages and I'll get back to you. Day 4, regularization techniques for model optimization. Let's start with understanding overfitting and underfitting. Even though we have done it so many times, let's dive deep into it. First, about overfitting. It occurs when a model learns the noise in the training data along with the patterns, leading to poor generalization on unseen data. Symptoms can be its high training accuracy but low test accuracy. It has large differences between training and validation losses. When does underfitting occur? It occurs when a model is too simple to capture the underlying patterns in the data. Symptoms can be low accuracy on both training and test sets. It's high bias in predictions. Let's talk about the regularization techniques. Regularization introduces a penalty term to the loss function during model training to prevent overfitting by discouraging overly complex models. We have the L1 regularization, also called as the lasso technique, which adds the absolute values of coefficients to the loss function. It encourages sparsity by setting some coefficients to 0, effectively selecting features. Next, we have L2 regularization, which is also called as the ridge technique, which adds the squared values of coefficient to the loss function. It shrinks coefficients towards 0 but does not set them to 0. And we have elastic net, which combines both L1 and L2 regularization. It's useful when there are correlated predictors and when feature selection is desired. Next, let's talk about the practical applications of regularization. First one is, of course, to prevent overfitting. It penalizes large coefficients, reducing model complexity. Another application is to handle multicollinearity, where ridge regularization is effective when predictors are highly correlated. Next application is feature selection. Lasso automatically performs feature selection by setting some coefficients to 0. Now, with this, let's jump into our hands on exercise for today, where we will be applying lasso and ridge regularization on a linear regression model, compare the performance, and analyze the effects of coefficients. We'll be using the California housing dataset, which is built in. So let's go and get started with first step to load and explore the dataset. Create a new file, save it as day 4 underscore exercise. And here I'm going to say from sklearn.datasets import, I'll say fetch underscore California housing. Next, I'm going to say sklearn dot model selection. I am going to import train test split. I think I might not need pandas or numpy, so let's go ahead and load the data set. To load the data set, I'm going to say California equal to fetch California housing. Next, I'm going to say X features and target equal to California dot data and California dot target. You can see I've not used data as I used to use before because I like the word California. Who doesn't? Next, I am going to say the feature names that we have here is California dot feature underscore names. Next, let's go ahead and split the data set. I can say X underscore train, X underscore test, Y underscore train, and Y underscore test equal to train test split X comma Y comma test size equal to 0.2 comma random state equal to 42. Probably I can sing a song with this now with the amount of times we have done this in the last 8 weeks. And next, let's go ahead and display data set info, where I will say print. First one is feature names. Now you see why I have created that feature names variable, because I can use it here. I can always have done that California.feature names, but sometimes it's better. /n, I'll say sample data /n, and I'm going to say PD. Okay, I do need pandas, so I'm going to say import pandas as PD, because I'm going to use the data frame X comma the columns that I'm interested is feature names dot head. Perfect. So this will show me some sample data. Let's go ahead and run it. I'm going to say Python day 4. Increase the size of this. And there you go. Feature names: medium income, house age, average rooms, average bedrooms, population, average occupation, latitude and longitude. And this is my sample data that I have from there. Next step is to train the linear regression model without regularization. So for that, first I will go ahead and from sklearn dot linear model import linear regression. Next, from sklearn dot metrics, I will import mean square error. So MSE is what we are using here. Next, I will go ahead and I mentioned train the linear regression model. For that, I need that model. I'll say linear regression model equal to linear regression. Next, I'm going to say lr dot model. Underscore model. I will fit and train it by x underscore train, y underscore train. So I give the training data for it to train. Now let's go ahead and predict and evaluate. I'm going to say y underscore pred equal to lr dot model, lr underscore model dot predict x underscore test and mse underscore lr equal to mean square error y underscore test and y underscore pred. Let's go ahead and print these data sets. So I'm going to say first linear regression MSE with no regularization. Hope I spelled it wrong or right, whatever, it doesn't matter. You got the point. MSE underscore LR. I'm going to say 0.2F. Display that. Next step, let's go ahead and print the coefficients. Now that is LR underscore model dot coefficients. Perfect. So I have that. Let's go ahead and test it out. I'm going to clear this out, run it again. Now my data linear regression model MSE is 0.56. Coefficients is, these are the coefficients that we have for this linear regression with no regularization. Next, let's go ahead and apply the ridge regularization. To do that, from my linear model, I will import ridge. So that's all that I need. And then I'll say train the ridge regression model. To do that, I'm going to say ridge underscore model equal to ridge. Now it needs a parameter of alpha, which I'll specify to 0.1. And then I'll say ridge model and then fit the data, which is x underscore train and y underscore train. Now let's go ahead and predict and evaluate. To do that, I'll say y underscore pred underscore ridge equal to ridge model dot predict and pass it x underscore test. Next, let's get the MSE for this ridge equal to mean square error, pass it y underscore test, and whatever we just got, y underscore pred of ridge. Now this will help us to first print the ridge regression MSE, which is MSE or MSE ridge and 0.2 F. Perfect. The coefficients for this, let's print that also. I'm going to say coefficients, since it's in matrix slash n ridge model dot coefficients. Now we can compare that. So we have too much data here. Let's clear it out and run it again. So this is our ridge regression. This is the linear regression MSE with no regularization 0.56. Even the ridge regression gave us 0.56 and the coefficients are displayed right over here. Next thing, let's go ahead and apply the lasso regression. Now lasso also I can get it from here, say lasso, and now I'm going to do the same thing. So I'm going to just copy it here. So I'll say lasso regression model. I will say this is lasso, and here I'm going to say lasso alpha equal to 0.1. Now lasso model fit x underscore train, y underscore train, perfect, print and evaluate. I'm going to say y predict lasso model predict x of test. MSE of lasso is mean square error, pass this and lasso here, and this is lasso MSE underscore lasso and lasso model dot coefficients. So that's it. So let's go ahead and run this and compare all of them MSEs together and coefficients together. I'll go clear it out, run it. So there you go, 0.56, 0.56 with lasso regressions is 0.61. I can always try to see if there is any change by increasing this float value. And you'll see 0.5559, exact same, whereas this is 0.6135. But you'll see the coefficients over here. There might be some differences here and there between linear and ridge, because we are adding regularizations in both ridge and lasso. So I hope you were able to follow along and get this. If you had any issues in here, let me know and I'll get back to you. But what we did here was we got the outcomes based without regularization, with regularization, and with lasso regularization. And just to summarize, today we went and understood what overfitting and how regularization helps to mitigate it. We learned the differences between L1, lasso, L2, ridge, and elastic net regularization techniques. we gain hands-on experience in applying the regularization techniques and comparing their effects. And finally, we develop the ability to choose appropriate regularization methods for different scenarios. So again, if you have any issues or questions, let me know. If you have any suggestions or recommendations or any questions in general, let me know in the messages and I'll get back to you. Day 5, cross-validation and model evaluation techniques. Today, we're going to look at or start with importance of cross-validation in model evaluation. So what is cross-validation? Cross-validation is a statistical method used to evaluate the performance of a model by partitioning the data into training and validation subsets multiple times. It helps ensure that the model's performance generalizes well to unseen data. Now, why use cross-validation? It prevents overfitting. By evaluating the model on multiple subsets, cross-validation provides a more robust measure of its performance. It's a reliable performance estimate. It reduces the variance of performance metrics compared to a single train test split, and it optimizes model selection, which helps in comparing and selecting the best model or hyperparameter configuration. Now let's talk about the types of cross-validation. We have k-fold cross-validation, which splits the dataset into k equal sized folds. Then it trains the model on k minus 1 folds and validates on the remaining fold. It repeats the process k times, ensuring each fold is used as a validation set once and is best for general purpose datasets. Next, we have the stratified k-fold cross-validation, which ensures that each fold maintains the same class distribution as the original dataset. It's particularly useful for imbalanced datasets. It's best for classification tasks with imbalanced data. Now, we have leave one out cross validation, which is LOOCV, which uses a single data point as the validation set and the rest as the training set. It repeats the process for each data point. Pros, it maximizes the training data for each fold. And cons, as you can assume, it's computationally super expensive for large data sets. And it's best for small data sets where maximizing the training data is critical. Next, let's look at the practical guidance on cross validation. So for choose k based on a dataset size, where k equal to 5 or k equal to 10 are commonly used for large datasets. You can use LOOCV for small datasets. Then you have stratification for imbalanced data. Always prefer stratified k-fold for imbalanced classification tasks to ensure the fair evaluation. And finally, combine with the hyperparameter tuning. Integrate cross-validation into grid or random search for robust hyperparameter tuning. With this in mind, let's jump into hands-on exercise where our objective is to evaluate a classification model using k-fold and stratified k-fold cross-validation and then compare the results to demonstrate the importance of stratification for imbalanced datasets. The dataset we'll be using here will be the credit card fraud detection dataset, which is available in the Google API's TensorFlow side as an imbalanced dataset. So let's go ahead and load and explore the dataset first. New file, Python file, save as day5 underscore ex. Now here, first I'm going to say import pandas as PD. Next, I am going to go ahead and load the data set. First, I'll get the URL. It is https://storage.googleapis.com/download.tensorflow.org/data/creditcard.csv. You can download it from there or view it on your browser. Let's say df equal to pd.read the CSV file from the URL above. So now once we have that, I'm going to go ahead and display the dataset info. I'm going to say print dataset info and then print df.info so we can look at the information. of why it's imbalanced, that actually can be found from here, which is the class distribution. So we can see how the distribution is between majority versus minority. So I'm going to say print df class dot value. The column name is also called class, so it's a little bit confusing here, but that's the fraud or non-fraud column. So I'll go to my terminal and say Python, my name of the project, day 5. It's going to first download it. It has a lot of data, so it takes a little while. So I'll pause it here and come back. And there you go. Once it's downloaded, we have the class distribution here, where you can see that non-fraud transactions is 284,315, whereas fraud transactions are 492. So you see, it's a highly imbalanced data set that we have. I'm going to clear it out, go back, and next, first step is to prepare the data. So I am going to go ahead and from sklearn dot model selection, I will import train test split, go here and say define the features and target. Now to get the features, I am going to say df dot drop columns equal to, I need to just drop one column, which is my target column. I'll say class, and next for my target, I just need to pick one, which is my class. So perfect, that we have it. Next, let's go ahead and split the data set. To split it, I'm going to say x underscore train, comma x underscore test, y underscore train, y underscore test equal to train test split, and to it I'll pass x, y, test size equal to 0.2, and my random state equal to 42. Save it. Done. Our next step is to implement the k-fold validation, cross validation here. So I'm going to go here and first from sklearn dot ensemble, I need the random forest classifier. So I'm going to say import random forest classifier. Next, we need the cross validation score and k-fold that is available in sklearn dot model selection. I think I already have model selection, so I can just say here cross val score, and I need k-fold, so get from there. Perfect. Next, let's go ahead and initialize k-fold first. For a k-fold, I'll say kf equal to k-fold, and I'll say number of splits that I want for this is 5. I want to shuffle the data, so I'm going to say shuffle equal to true, and then random state equal to 42. So that initializes your k-fold. Next, let's go ahead and train and evaluate the model using the random forest classifier. So I'm going to say rf underscore model equal to random forest classifier, random state equal to 42. Next, I'm going to say scores underscore k-fold equal to cross val score. So cross validation score function, I'll pass it rf model. We'll have to pass the model, we have to pass the training data set, we have to pass the y training data, x train, y train, and cv equal to, I'll pass a cross validation is k-fold, so I'm going to give kf here, and scoring equal to, I need accuracy for that, so that's why I specify accuracy. Once I'm done with this, let's go ahead and print and see our results. F k dash fold cross validation scores equal to, our scores underscore k fold, that's where we can print it from, and then print f mean accuracy for k dash fold is, I can say scores k fold dot mean colon 0.2f. Don't want to see the extra decimals. And next step that we have to do, so this will print those out, but our next step that I want to do is I want to implement the stratified k-fold cross validation and then compare both of them together. So for that, from model selection, I will also call for stratified k-fold. Now I'm going to go here, first initialize the stratified k-fold. I will say skf equal to stratified k-fold, and to this I'm going to use the same number of splits as 5. I say shuffle equal to true and random state equal to 42. So everything, all the parameters are exactly same. Now let's go ahead and train and evaluate the model. For that, I'll say scores underscore stratified equal to cross validation score. Pass it the model, RF model. I'll pass it x underscore train. I'll pass it y underscore train. I will pass the cross validation is skf that we've created above, and scoring equal to accuracy. So exactly same, but the CV is different here. Now let's go ahead and print the same thing, where instead of this I'm going to say stratified k-fold validation scores, and this one is not k-fold but stratified, and then I can say mean of stratified k-fold, and here I can say stratified and get the mean. Now that I have everything together, I can go ahead and compare these values. So I'm going to go back here and run it. So it took a little bit time, and finally we have our results here. We have the information about the data set, the class distribution as I mentioned, and here is our data after using the k-fold cross validation scores, which provides accuracy scores across folds but may suffer from inconsistent class distribution from imbalanced data sets. It has a pretty good accuracy, as you can see, 0.93962, but as compared to stratified, it has 0.99967. So it's a little better when you use the stratified k-fold cross validation scores as compared to k-fold, especially for a imbalanced data set. And it maintains, the reason is why stratified k-fold cross validation maintains class distribution across folds, leading to more reliable and consistent performance metrics. To summarize, today we went and understood the importance of cross validation for evaluating machine learning models. We looked at the differentiation between k-fold, stratified k-fold, and leave one out cross validation. We gained some practical experience in implementing the k-fold and stratified k-fold cross validation, and we learned how to choose the appropriate cross validation method for different data sets and tasks. So if you have any questions or had any issues implementing this, let me know and I'll get back to you. Day 6. Automated hyperparameter tuning with grid search CV and randomized search CV. Here we're going to start with using grid search CV and randomized search CV from scikit-learn. So what is grid search CV? Grid search CV performs an exhaustive search over a specified parameter grid. It trains and evaluates a model for every combination of hyperparameters in the grid using cross-validation. Next, what is randomized search CV? Randomized search CV selects a fixed number of random combinations from a parameter distribution. It is faster than grid search CV for a large hyperparameter spaces while still providing a good results. Let's talk about the key features. For first, I want to talk about automates the hyperparameter tuning. It combines model training, evaluation, and hyperparameter search into a single step. Another feature is cross validation integration. It ensures robust performance metrics by using cross validation. And it also does result interpretation, provides the best hyperparameter combination and associated metrics. Let's talk about how to integrate cross validation with hyperparameter tuning. First, cross validation, it ensures that the hyperparameters selected generalize well to unseen data. The benefits of this is it reduces overfitting
to the training dataset, and it provides robust estimates of model performance. Next, let's talk about interpreting results and selecting the best model. So best parameters is access the optimal hyperparameter combination using dot best params underscore on the underscore attribute. Next, you have the best estimator. You can retrieve the model trained with the best hyperparameters using the dot best underscore estimator underscore. And you can get the performance metrics. You can use the dot best score underscore to evaluate the performance of the best hyperparameters. Let's use all this inside our hands-on exercise where the objective is to use grid search CV and randomized search CV to tune hyperparameters of gradient boosting and support vector machine models and compare the results. For the dataset, we'll be using the iris dataset, a multi-class classification problem. And to start with, let's create a new file. I'm going to call it day6 underscore ex. And inside here, our first step is to load and prepare the dataset. So for that, let's get the dataset sklearn.datasets import load iris. You can use your own dataset if you want to, but all you have to do is change these things. sklearn.model selection, and I will import from there train test split. So let's first load the dataset. To load the dataset, I'm going to say data equal to load iris. Next, I'll say x, the features, and the target y equal to data dot data. So that will assign my x, and for my targets, I say data dot target, which will be assigned to y. Now let's go ahead and split the data set. To do that, I'm gonna need x train, x test, y train, and y test. Now this can be fetched from train test split, which will split x, y, test size of 0.2 and random state equal to 42. There you go. Next, let's go ahead and print dataset loaded and split successfully. I am just going to print that for now. I'm not going to display anything, but you have now loaded and prepared the dataset. Now, next step, which is part one of the entire thing, is to do the grid search CV with gradient boosting. So first, for that, let's go ahead and from sklearn.ensemble, I will import gradient boosting classifier, and from the model selection, I will get the grid search CV. I can also get the randomized search CV already, since it's in the same class. So next, I will go ahead and define my parameter grid. The parameter grid will be called parameter underscore grid equal to. Inside this, let's start with n underscore estimators, which I'll give the values of 50, 100, and 150. Next, I need the learning rate. Let's say learning underscore rate. For that, I'll say 0.01, 0.1, 0.2. Next, I need the max depth of the trees, max underscore depth. For that, I'll say 3, 5, 7. Perfect. I have that. Next thing is, now let's go ahead and initialize the grid. Initialize the grid search. So for that, before even initializing grid search, let's initialize the grid search CV. So for that, I'll say grid underscore search equal to grid search CV. To that, I'll give the estimator that I'm going to use, and for that I have gradient boosting classifier, random state equal to 42. Next, I'll give the parameter grid for it, which is
parameter grid. Next, I'll give the scoring, which I want to do with accuracy. Next, I want to say cross validation equal to 5, and number of processors is use all the processors that are available by setting -1. Now let's go ahead and perform the grid search. So I can do the grid search by fitting x underscore train and y underscore train. So this will perform my grid search. Next, I'm going to get the best parameters and score. So for that, I'll say best underscore params underscore grid equal to grid search dot best parameters. Next, I want to get the best score underscore grid, that will be grid search dot best score. If I want, I can print them out. Best parameters for grid search CV are best parameters grid. Next, I'm going to say print f best cross validation accuracy for grid search CV is best underscore score grid, and I can say 0.4f. So that's our first part. Next, let's go and evaluate the best model on the test data. So I am going to, from metrics, do I have metrics? No, from sklearn dot metrics, I will import accuracy score and classification report. So now let's get the best model. Get the best model. To do that, I can say best grid underscore model equal to grid search dot best estimator. Next, I'll say predict and evaluate based on that model. I can say y underscore pred underscore grid equal to best underscore grid underscore model. I want to predict, and I pass the data set x underscore test, and I'll get the accuracy of this grid by calling the accuracy score y underscore test and use that y pred that we just got from the grid. Now let's say print test accuracy for grid search CV is accuracy grid 0.4f, and I'll print /n the classification report /n is my classification report, and to it I'll pass y underscore test and y underscore pred grid. Perfect. So I have everything available here. Now the second part of it, which is the randomized search CV with support vector machine. To do that, I am going to first go ahead and from sklearn I.svm, because we want the support vector machine that I can import from here as svc. Next, I want from model selection. I've already done randomized search CV. I also might need numpy for some operations. I'm going to say numpy as np. Okay, so now I'm going to go ahead and first define the parameter distributions. Now, why do we have numpy is the question that you're asking. Now, this is, I want to create a parameter distribution here with our first element, which is C, as np dot log space, and then here this is the reason why I'm using numpy from -3 to 3, and I need 10 elements, so that's what I have. Next I need is the kernel. For the kernel, I am going to say either use linear, or you use RBF, or we can use poly, or you can use sigmoid. So use one of these as kernel. And then for gamma, I want to use either scale, or we can do auto. So these are my parameters for distribution. Now let's go ahead and initialize the randomized search CV. To do that, I'm going to say random underscore search equal to randomized search CV, and to that I'll pass the estimator. In this case I have the SVC, that's what I want to use. Random state equal to 42. I'm going to say parameter distributions equal to whatever I created above, parameter distributions. Next, I want to say how many iterations I want to run. Let's run 20. I think it might be too much. This is number of parameter combinations to try, but why not? Scoring equal to accuracy, cross validation equal to 5. Number of jobs or number of processes that I want to use is -1, which means all of them. Random underscore state equal to 42. Perfect. So I have this. Next step is to perform randomized search, which is to train the model. So I'm going to say random search dot fit, pass x underscore train and y underscore train. So this will give us the best parameter. So let's go ahead and get the best parameters and score from this. To do that, I'm going to say best parameters. We did grid before. I'm going to do now random equal to random search dot best parameters. Next, I need the best underscore score, not grid but random search dot best score. Perfect. So I have both of them. Now let's go ahead and print first best parameters for randomized search CV, which is best underscore params underscore random. Perfect. Next I'll go say print best cross validation accuracy for randomized search CV is best score random 0.4f. Is it same as what we did before for this? Yes, 0.4f, 0.4f. Okay, perfect. So I've done that. Now we can go ahead and evaluate the best model on the test data that we have. To do that, I'm going to first say get the best model. I'm going to say best random underscore model equal to random search dot best estimator. So this will give me the best model that is trained with the data that we have. Next, let's go ahead and say predict and evaluate. I'm going to say y underscore pred underscore random equal to best best random model dot predict. Make sure you don't select the wrong one, or else you'll have the same answer. X test accuracy underscore random is accuracy score y underscore test and whatever y underscore pred random that I just got. Perfect. Now let's go ahead and print f test accuracy for randomized search CV is accuracy random 0.4f. Perfect. Last slash n classification report slash n is classification report. Use the y test and y spread random. Perfect. Now we can go ahead and compare all these items together and see which one is the best. So now go ahead, save it, and say python day6.ex. It's going to say dataset loaded and split here, which was our first output right over here. Lots of lines of code here. Line number 16. Next, it's going to give me the best parameters for grid CV, which was printed right here. And it said learning rate is 0.1 based on the data that is set, max depth 3, and estimate is 50. Best cross validation score is 0.95 here, 0.9583 for the randomized search CV. So you see the difference right away, 95 versus 9583. So in this case, the best one that we can use is here. But if you look at the accuracy here, is 0.9667, whereas the test accuracy with grid search CV is 1. So again, depending on which data set you're providing, what you're giving it, grid search CV provides high accuracy by evaluating all the hyperparameter combinations, but is slower for larger parameter grids, whereas randomized search CV achieves comparable accuracy with fewer evaluations, offering faster results for large hyperparameter spaces. So they both have their pros and cons, but depending on what you want to use, you can use either or. And I hope you are able to follow along and get this output. If not, let me know and I'll get back to you. So just to summarize, today we learned how to use grid search CV and randomized search CV for automated hyperparameter tuning. We understood how cross-validation integrates with hyperparameter search for robust evaluation. We developed the ability to interpret the results, select the best model, and compare the tuning strategies. And we finally gained hands-on experience tuning both gradient boosting and support vector machine models. So if you had any issues while implementing this or have any questions, let me know and I'll get back to you. Welcome to our day 7, the last day of this particular week. So today we are going to look at our optimization project where we'll be building and tuning a final model. So first, let's start with applying all the learned tuning and optimization techniques. So let's look at the comprehensive list of model optimization. We have data preprocessing, where we ensure data is clean, scaled, and encoded appropriately. Then we do feature engineering, which is derive new features and select the most important ones. Then we follow regularization, where we avoid overfitting by penalizing complex models. Next, we jump into the cross validation, where we use techniques like k-fold or stratified k-fold for robust performance metrics. And finally, we look into hyperparameter tuning. We use methods like grid search CV, randomized search CV, or even Bayesian optimization for this. Next, let's look at evaluating and interpreting the model performance. For performance metrics, we use for classification, we use accuracy, precision, recall, F1 score, and ROC AUC. For regression, we use mean square error, MSE, or mean absolute error, MAE, or R square. And importance of interpretability, we use feature importance and coefficient analysis for transparency. So I hope you were able to follow along this entire week and understand all these different concepts. So now with that, let's jump into our hands-on project where the objective is to build, tune, optimize a machine learning model using a structured process and evaluates its performance comprehensively. The dataset we'll be using will be the customer churn dataset that we have used before, a classification problem to predict whether customers will churn. So I already have that available in my folder called telco customer churn. This is the data set. It has all the different fields about the customer, and at the end, will the customer churn, yes or no? That's what we are trying to predict with our data set or train the model on that. So first step again is to load and explore the data set. Now start a new file, save it as day7 underscore exercise, and here first let's start with import pandas as PD. Then I'll load the data set. For that I'll say data frame equal to PD dot read CSV, and I'll give the name right here. Then let's go ahead and display the data set info. For that first I'll say print data set info /n. Make it look pretty. Print df.info, display the info. Next I'm going to say I want to see the class distribution /n class distribution /n, and I'll say print df of churn, as we saw, that's the last column, dot value counts. So that will give me the class distribution of how many will churn and how many will not, and see if it's a unbalanced data set. /n sample data. Let's also see some sample data for this, and I'll say for that I want to see df dot head. Perfect. Let's go ahead and run this. There you go. Make sure that we have proper alignment, because Python doesn't like if you don't align your code properly. Let's say Python day7 underscore exercise, run it, and here's our data set with all the different columns. Churn is what we are interested in, and if you see the class distribution, no is 5174, yes is 1869. It's unbalanced, but not that much, but it is unbalanced data set where this is 3 times more than this value here. And we have our sample data, which displays customer ID, gender, senior citizen, dot dot dot, monthly charges, total charges, and churn. So we have 21 columns and 5 rows to be displayed right here. Next step is to pre-process the data. We will handle the missing values and encode categorical. So in this particular case, I don't see any missing value, but if you are using a data set that has missing values, so you'll have to do that. And we also do encode the categorical variables, and finally we'll scale the numerical features. So let's go ahead, and right here I'm going to say from sklearn dot pre-processing, I will import label encoder, and I will import standard scalar. Once I have that, I am going to handle the first is missing values. Now to handle the missing values, I am going to, let's pick a couple of columns. I'm going to pick total charges. Let's go here, total charges, and to this I will say PD dot to numeric and df of total charges, comma, I'll pass errors equal to course. Okay, so there you go. So that will take care of the errors. And next I'm going to say df of total charges dot fill. Okay, so this is changed. I always use the older method. I'm going to say fill NA, and to this I'll first have to select the column which is total charges. The value that I want to assign to this is df of total charges dot median, and then I'll say in place equal to true. So there you go. So we have assigned, we filled the if there's any data that is missing, it will be filled, and then I'll say encode the categorical variables. To do that, I will say label underscore encoder. I'll create a label encoder, and that is label encoder that we have imported. And then I'll say for column in df dot select for for column in df dot select underscore d types, I will say include equal to, if it's object, which means it's categorical, dot columns. Then I will check if the column is not equal to, I'm not interested in churn, so that I will ignore here. I'll say df of column equal to label encoder dot fit transform df of column. There you go. That'll take care of all of them. So this will encode the categorical parameters variables. Now next I'm going to go ahead and encode the target variable. So df of churn, I will say label encoder dot fit transform, and this one I'll say df of churn. There you go. So that will take care of churn, my target variable. Now let's go ahead and scale the numerical features. So they are uniform. So for that I'll say scalar equal to standard scalar. Standard scalar, and I will say next is numerical underscore features that I'm interested in is, let's pick some. So from here I'm gonna pick tenure, I'm gonna pick the monthly charges, which is float, and I'm gonna, since I have total charges, I have changed it, so I'm gonna use total charges here. That will complete converted to numeric. df of now numerical features equal to scalar dot fit underscore transform df of numerical features. So this should scale all the numerical features. Now let's go ahead and get my features and target, that I can say by saying x equal to df dot drop. I want the entire set except I am not interested in churn. So that's what I'll specify here, and y equal to, I'll say that I am interested in churn alone. Perfect. So this takes care of pre-processing the data. Next thing we'll do is train, test, split, and initialize the model evaluation. So that's our next step. So for that, I'm going to go here. I don't have model selection, sklearn dot model selection. I will import from there our favorite one, which is train, test, split. Next, from sklearn dot ensemble, I will import the random forest classifier, and for metrics sklearn dot metrics, I will import accuracy score classification report. Next, let's go ahead and split this data set. So I'm going to go here and say split data set, and for that I'll need xtrain, xtest, ytrain, and ytest as my variables, which will be filled by trend test split x comma y comma test size equal to 0.2 comma random state equal to 42. Let's look at it. Perfect. Next, I am going to go ahead and train the initial model. To do that, I'll say rf underscore model equal to random forest classifier random state equal to 42. I'll say rf underscore model dot fit x underscore train and y underscore train. Now once I have trained that, I'm going to go ahead and evaluate initial model where we'll add y underscore pred equal to rf underscore model dot predict. And then here I'll pass x underscore test to this and get my accuracy for the initial model, which I'll say accuracy score, and to it, did I spell? Yes. I'll give y underscore test and y underscore pred. Perfect. So I have evaluated, or I got all the data. So now let's go ahead and print stuff out. I'll say initial model accuracy is accuracy initial 0.4 f. Next I'll say print /n classification report /n. In this particular case, I'll call the classification report function and pass y test and y underscore pred that we just got. Perfect. So that should take care of that. Now that we have trained, test, and split, and also initial model evaluation, let's go ahead and do the hyperparameter tuning with the randomized search CV. So for that, from my model selection, I would need randomized search CV. I also need, for creating random values, numpy as np. Now I'm going to go ahead, as you remember, first thing is to define the parameter grid. My parameters with distributed parameters equal to, I'm going to say first I need n estimators. np dot range, to it pass 50, 200, and 50 to 210 of these. Next I'm going to say my max underscore depth is either none or use 5 or use 10 or use 15. Next I'm gonna set the minimum samples split, that can be 2, 5, 10, 20. Next I will use my minimum underscore samples underscore leaf 1, 2, and 4. Perfect. So I have my parameter grid. Now next I'm going to go ahead and initialize my randomized search CV. To do that, I'm going to say random underscore search, create a variable, and say randomized search CV. To this I need a lot of different parameters that it needs. One is estimator, is we said that we'll use the random forest classifier, use that. Random state equal to 42. Next I need the parameters distributions, which is I've just created just now, so I'm going to use that, which is created right here. That's what I'm using here. Next, number of iterations that I want to run. I want to run 20 iterations. This is the number of parameter combinations to try, that is CV equal to 5, or cross validation I will say scoring equal to accuracy, and I'll say jobs, which is processors. Now you can always, when I'm typing here, it shows me what they are, gives me descriptions, what are the different values that are there. So n of jobs, as I said, is the number of processors that I'm using, which will kind of be specified when I select this. It should show, but I'm setting -1, which means all the processor, and random state equal to, so it talks about what random state is, how to use it. It has all the different documentation right over there, equal to 42. So that's my initialization of random search CV. Next, I am going to go ahead and perform my randomized search. To do that, I'll say random search dot fit, easy enough, x underscore train and y underscore train. So this will run that. It will take some time, and then finally get the best parameters from the list that we have created. I'm going to say best underscore params equal to random search dot best params. Then I'm going to say print f of best parameters on randomized search CV is the best parameter that I just got above. Perfect. So I'm going to print that out. Now, our next step is to evaluate the tuned model. So for that, let's train the best model available, which is the best model. Let's pick it up. Random search dot best. Out of all the estimators that you have, give me the best estimator. Now I'm going to say predict and evaluate that. To do that, I'm going to say y underscore pred underscore tuned equal to best model that we just got. From that, predict the values from xtest. Now let's check the accuracy. I'm going to say accuracy tuned equal to accuracy score y underscore test and y underscore pred tuned. Now based on that, now let's go ahead and say f of tuned model accuracy is accuracy tuned 0.4f. Next, let's get the classification report. /n classification report for the tuned model is /n comma classification report. Now you know what it needs: y underscore test and y underscore pred tuned. So this will give me the classification report. And now just one more step, to use the cross validation for final performance metrics. So from model selection itself, I am going to pick cross val score, and here just two more lines of code, I promise. So I evaluate the also not counting comments as code, using cross validation, and here I am going to say CV underscore scores equal to cross val scores. I'm going to use my best model that I got,